This video explores a paradigm shift in AI architecture, moving away from the single know-it-all agent and towards a collaborative ecosystem of specialized agents. This is similar to how a successful company operates. It doesn't hire one generalist to perform every job function. Instead, it builds a team of specialists, accountants, marketeers, engineers, and project managers who collaborate to achieve a common goal. This multi-agent system, or MAS approach, offers enhanced modularity, specialization, reusability, and maintainability, paving the way for more sophisticated and robust AI applications. Throughout the session, we will construct a practical, real-world application that embodies this multi-agent philosophy. A financial analysis system. The system is designed to answer a high-level user query, such as give me a summary of Google's recent stock performance in any relevant company. A monolithic agent would struggle with this task, needing to parse the query, know how to access multiple disparate financial data APIs, fetch the data, and synthesize a report. Our system will instead deploy a team of specialized agents. First one, an orchestrator agent. This agent acts as a project manager. It receives the user's high-level goal, breaks it down into subtasks, and delegates them to the appropriate specialist. The second one is the data gathering agent. This agent is the domain expert for financial data. Its sole purpose is to fetch specific piece of information like stock prices or news articles when tasked by the orchestrator. And the last, the data server. This isn't an agent but a crucial piece of infrastructure. It routes the raw financial APIs, exposing them as a standardized, easy-to-use tools that the data gathering agent can leverage. This hierarchical and decoupled structure is a common and powerful pattern for building complex agentic systems. To build a system, we rely on a stack of three powerful open technologies. Understanding their distinct role is fundamental to everything that follows. MCP, Model Context Protocol, is our universal toolbox. Initiated by Anthropic, MCP standardizes how an agent connects to an external tools, data sets or data sources, and even APIs. It functions like a USB-C for AI. Instead of writing custom integration code for every tool, an agent can use MCP standard to plug into any MCP compliant service, discovering and using its capabilities on the fly. Next is A2A, our agent-to-agent protocol. This protocol is our corporate language, introduced by Google, 50 partners. A2A is an open standard that defines how different AI agents, even those built with different frameworks or different vendors, can discover each other, or delegate tasks, and collaborate securely. It is the foundation for creating interconnected agent society. Next is ADK, or the Agent Development Kit. This is our agent workshop. ADK is an open source code-first framework from Google designed specifically for building, orchestrating, and deploying sophisticated agents and multi-agent systems. It provides the practical tools and abstractions to implement the concepts defined by A2A and MCP protocols, transforming agent development into a structured software engineering discipline. The primary challenge in making AI agents useful in the real world is connecting them to live data and actionable tools. Without a standard, every integration, whether to a database, a third-party API, or an internal service, it'll require custom brittle code, and this creates a maintenance nightmare where a small change in an external API can break the entire agentic application. The MCP was created to solve this agent-to-tool problem. MCP operates on a simple yet powerful client-server architecture. An MCP host is the application that wants to use a tool, which in our case will be an agent built with an ADK. The host runs an MCP client, which is responsible for communicating with the server. An MCP server is a lightweight program that wraps a data source or an API, exposing its capabilities through the MCP standard. This communication is standardized using the JSON RPC 2.0, a simple and well-established remote call procedures protocol typically transmitted over HTTP. This reliance on a familiar web standard greatly simplifies implementation and adoption. An MCP server can expose three main types of capabilities. A resource, which can be contextual data, like the content of a file or a database record that can be provided to an LLM. It can be prompts, reusable templated workflows or messages, or it can be tools, executable functions that the AI model can choose to call. Our focus in this class will be on exposing and consuming tools. A critical aspect of real-world system is security. MCP provides the necessary framework for secure interaction, but does not enforce a specific implementation. The protocol specifications outline that a developer are responsible for implementing robust user consent flows, data privacy controls, and tool safety measure. For example, an MCP server can be configured to require API keys or an authentication tokens for authentication. And it can implement rate limiting policies to prevent abuse. This design provides the flexibility needed for diverse enterprise environments while underscoring the developer's responsibility to build secure and trustworthy systems. A2A is built on few core concepts that facilitate inter-agent communication. The agent card. This is an agent's machine-readable business card, typically a JSON manifested server over HTTP. It describes the agent's identity, its capabilities or skills, the communication protocol it supports, for example, the HTTP endpoints, and any authentication requirements. Agent cards enable dynamic discovery, allowing an agent to find other agents that can help it achieve a goal without prior hard-coded configuration. Next is the task itself. A task is the fundamental unit of work in A2A. When one agent wants another to do something, it creates a task. The task has a unique ID and a life cycle. Example, submitted, it could be in progress, it could be completed, or failed, which is essential for managing asynchronous, long-running operation that are in common, complex workflows. And finally, the communication. Like MCP, A2A is built on establishing web standards, primarily using JSON RPC 2.0 over the HTTPS for request and response. It also explicitly supports streaming of updates via server-sent events or SSE and asynchronous push notifications, webhooks, making it highly flexible for different interaction patterns. A common point of confusion is why two separate protocols, A2A and MCP, are necessary. They might seem to overlap, but they are designed to be complementary, addressing different layers of the agentic stack. This separation of concerns is a fundamental principle of robust software architecture and is key to building scalable and maintainable multi-agent systems. MCP is fundamentally about capability. It standardizes the vertical connection between an individual agent and the tools and the data sources it needs to act in the world. It answers the question, what can this agent do? An agent uses MCP to interact with non-agentic resources like API, databases, or file systems. A2A, in contrast, is about coordination. It standardizes the horizontal communication between peer agents. It answers the question, how do we work together? An agent uses A2A to discover, delegate to, and collaborate with other autonomous agents. This layered design creates a powerful and flexible architecture. In our financial analyst system, orchestrator agent doesn't need to know how to get the stock prices or even what MCP is. It only needs to know via A2A that a data gathering agent exists and can fulfill a get financial data task. The data gathering agent in turn doesn't need to know the ultimate purpose of this request. It just needs to know that it received a task via A2A and that it has a set of tools accessible via MCP to complete it. This relationship is not competitive, it's synergistic. MCP makes an agent capable, A2A makes the collaborative. A robust multi-agent system will almost use both. With a conceptual understanding of MCP and A2A protocols, the next question is practical. How do we build agents that can speak these languages? This is where Google's Agent Development Kit comes in. ADK is an open source code-first Python framework designed to bring these agentic concepts to life. The core philosophy of ADK is to make agent development feel more like traditional software engineering. It emphasizes modularity, testability, versioning, and clear explicit logic defined in code rather than opaque prompts. This approach is crucial for building enterprise-grade applications that are reliable, maintainable, and transparent. ADK provides a comprehensive set of features covering the entire development lifecycle. The framework is built from the ground up to support composition of multiple specialized agents into a collaborative hierarchies, offers component for both deterministic, predictable workflows and dynamic LLM-driven routing. ADK has built-in support for a variety of tools, including custom Python, OpenAI specifications, and critically for our purposes, first-class integrations with MCP. It includes tools to systematically assess agent performance, evaluating not just the final output, but the entire execution trajectory. ADK is designed for production, with clear paths to containerize agents and deploy them anywhere, from local machines to scalable managed platforms like Google Cloud Run or Vertex AI Agentic Engine. All agents in ADK inherit from a common base agent class, which provides a fundamental blueprint. From there, ADK offers several specialized agent types to suit different needs. The first one is LLM agent. These are the reasoning engine of the system. An LLM agent uses a large language model like Google's Gemini as its core for understanding natural language, planning, and dynamically deciding which tools to use. They are ideal for flexible and non-deterministic tasks that require intelligence and reasoning. A basic LLM agent can be defined with just a few lines of code specifying a model, a name, and a core set of instruction. Is workflow agents. These agents are designed for orchestration and control flow. Unlike LLM agent, they do not use an LLM to decide the execution path. Instead, they control the flow of other agents in a predefined deterministic pattern, either in sequence, in parallel, or in a loop. This is crucial for building predictable and reliable pipeline where the steps are known in advance. For example, sequential agent could be used to ensure that a data gathering step always completes before a data analysis step. The tool parameters are key feature of LLM agent, and this is a list where capabilities are attached to the agent. These can be simple Python functions decorated with the NAT tool, or entire toolset from libraries like LangChain, or as we see, an MCP toolset that connects the agent with an external MCP server. This mechanism is how we equip our reasoning agents with ability to perform actions. Before writing any code, a proper development environment must be established. This is a standard practice in software development that ensures dependency isolation and reproducibility. From a terminal, a new virtual environment needs to be created and activated. This sandboxes the project's dependency from system's global Python installation. Next, the core libraries for our projects are installed using pip. This includes the agent development kit itself, the Google's ADK, and the SDK for agent-to-agent protocol, the A2A SDK. Additional libraries for web UI like Streamlit and MCP servers are also needed. Feel free to use the code from the GitHub link that I've shared in the description. Next is about project structure, which is essential for maintainability. This project will be organized into logical directories mirroring the architecture of our system. This structure separates the agent definitions, the MCP server logics, and any reusable utility code, making the project clean and easy to navigate. This mirrors the best practice of modern software development and the inferred structure of a production-grade. Before diving into the code, it's crucial to have a clear architectural blueprint. This diagram on screen illustrates the flow of information and control within our system. A user interacts with a simple web UI, which sends their request to an orchestrator agent. The orchestrator agent then delegates the data fetching subtask to the data gathering agent using A2A protocol. The data gathering agent then uses MCP protocol to call the necessary tools exposed by our financial data server, which in turn communicates with a third-party financial API. Our first component is the MCP server. Its job is to abstract away the complexities of a third-party API, in this case, the FinHub API for financial data, and expose its functionality as a simple standardized MCP tool. This decouples our agent from specific implementation details of the data source. We will be using the fast MCP library, a convenient wrapper for creating MCP servers in Python. In this file, we define two Python functions, the get current stock price and the get company filings function. The add tool decorator from FastMCP automatically handles the work of converting these functions into MCP compliant tools, complete with schemas derived from function signatures and docustrings. Finally, we instantiate an MCP server with our list of tools and run it. The server will now listen for incoming MCP requests. Let's look at the foundation of our agent, which is the ADK base agent Python file. And this kind of defines the ADK agent, an abstract base class that all of other agents will inherit from. It provides a standardized structure and a rich set of built-in features. The init method, it sets up several properties like the name, the description, the capabilities, versions, and a hard-coded ADK version. It also initializes the agent's state to idle, creates an empty memory dictionary, an empty execution history list, and assigns a unique agent ID using the UUID function. This gives every agent instance a distinct identity and state from the moment it's created. The process underscore task method is an abstract method. This is a contract. It forces any class that inherits from the ADK agent to implement its own process task logic. This is where the unique work of each agent will be defined. The execute method is the heart of the ADK framework. It's a wrapper around the process task call. When an agent is asked to perform a task, the execute method is called. It first sets the agent state to processing, logs the start of the execution, and then calls the agent-specific process task method. After getting the result, it enriches it with block of ADK metadata, including the agent's ID, execution time, and a final completed state. It includes a robust try-except block for error handling. If anything goes wrong during the process task, it catches the exception, sets the state to error, and returns a structured error message. The other methods are straightforward helper functions or methods. The get capabilities and the get state return their respective properties. The get ADK info returns a comprehensive dictionary of the agent's current status. The log execution is a private method for logging, which appends a small log entry to the execution history and keeps it trim to the last 100 entries. And finally, the update memory and get memory provide simple key value storage for the agent to maintain information across the task. Let's take a look at the ADK data gathering agent. This agent's job is to fetch financial data. It inherits from the ADK agent, and its init calls the super init to set up all the base agent features. It also defines an ADK symbol registry, which is a dictionary that maps company names like Apple or TechTarget to their the core process task. It receives a payload dictionary, extracts a query, and immediately calls the extract ADK symbol. This private method first checks the ADK symbol registry for a match in the query. If it doesn't find one, it uses a regular expression to find an uppercase string between 1 and 5 characters long, assuming it's a symbol. This provides a two-tiered approach to identifying the targeted company. Once it has a symbol, the process task calls the get ADK company info and the gather ADK financial data. The get ADK company info is a simple function with hard-coded data for a few specific symbols like TDGT, APL, and FRH. It returns a dictionary of company details, acting as a small internal database. To gather ADK financial data is where the MCP implementation is used. Its first attempt to make an HTTP post request to the local 8001 call. This is our financial data server. It sends the tool name get stock data and the symbol as arguments. If the request is successful, it returns the data received from the MCP server. If the request fails for any response, like a timeout or a connection error, the accept block catches the error log, logs it to the agent's memory, and then the code falls back to returning hard-coded data for a specific symbol. This makes the agent resilient. Finally, the process task assemble all this gathered information, the symbol, the company info, the financial data, and some market context from another helper into a single dictionary and returns it. The A2A server PY file defines a server that wraps each of our ADK agents, allowing them to receive tasks over HTTP. This is a server-side implementation of A2A communication. Essentially, there are two main classes, the class ADK Task Manager and the class A2A Server. The ADK Task Manager class manages the lifecycle of a task. Its create and run task method is where the action is. It's called when a new request comes in, and it generates a unique task ID, creates a task dictionary to task the state, and then critically, it calls self.adk agent execute payload. This is the link the A2A server receives an HTTP request and calls the execute method of the ADK agent it's managing. It waits for the result, appends it to the task message history, marks the task as completed, and returns the entire task object. The A2A server class wraps this up in a Starlet web application. In its init, it creates a Starlet app, enabling coarse middleware to allow web frontends to connect, and instantiates the ADK task manager, passing it the specific ADK agent instance that the server will host. It then sets up several routes. The main route handles post requests and passes them to handle ADK request, which in turn calls the task manager's create and run task method. This is the primary entry point for A2A calls. The well-known agent JSON route an agent card, which is a standard way for agents to advertise their capabilities. The ADK info and the ADK capabilities are custom endpoints that expose agents' internal state and capabilities by calling the get ADK info and get ADK capabilities method on the agent's instance. In short, you run one instance of this A2A server for each ADK agent, giving its own API endpoint for communication. The ADK orchestrator agent.py file. This is the brain of the operation, controlling the overall workflow. It acts as the client for A2A communication. It inherits from ADK agent in its init method. Is super simple, but it defines a crucial piece of data, the agent endpoints dictionary. This dictionary maps the names of the worker agents to the URL of their A2A server instances. The entire workflow is defined in the process task method. It first defines a list of tuples called workflow steps. This list represents the entire financial analysis process, gathering the data, then the quantitative analysis, and finally the report generation. It defines a sequence of operations as well. The code then iterates through this list inside the loop for each step. It calls self.call ADK agent. Let's take a look at this method. The call ADK agent is the A2A client implementation. It takes the agent's name and a payload, and it looks up the agent's URL from the agent endpoints dictionary that we previously saw. Then it constructs an ADK message dictionary that follows the A2A specification with role and part fields. The payload for the target agent is a JSON encoded placed inside the text part. It then uses the request.post library to send this message to target agent's A2A server. It also includes retry logic. If the retry fails, it'll wait a second time and try again up to 3 times. This makes the orchestration more robust. Back in the process task, after the loop has successfully collected results from all the worker agents, it calls the synthesize ADK result. This method digs into the complex nested JSON returned by the report generation agent, then extracts the final report data and formats into a clean top-level dictionary. The process task method then returns the final payload containing the results from every step of the workflow as well as the synthesized final report. This is the final output of the entire multi-agent system. Now with all the components built, it's time for the live demonstration, and this requires running each of our services in a separate process. Run the MCP service in one terminal, run the data gathering agent A2A server in one, and start the web UI in another. And so this was the web app that we built, and to start off easy, I think you can just clone the GitHub repo and try running this on your end, which kind of has pages to show all the agents and if they're up and running, and the history of the prompts that you give. And finally, let's kind of go in and try running. Now let's try running this for Apple. Once we kind of hit on the analysis button, it goes through the different stages that we've defined in the code, from data gathering to quantitative analysis to qualitative analysis, and finally the report generation. And in terms of the results, it just gives you a high-level overview of the Apple stock with a recommendation on whether you should buy it, hold it, or sell it, with the confidence level, and just a high-level overview of some insights of how it's performing in the market, and also some financial highlights as well. A local demonstration is a great proof of concept, but real-world application requires a more robust deployment strategy. The architecture we've chosen lends itself perfectly to a modern cloud. The first step is to package each independent service, the MCP service, the data gathering agent, and the orchestrator, into its own Docker container. This encapsulates its code and dependencies and ensures it runs consistently in any environment. These containers can be deployed as independent, scalable microservices on a platform like Google Cloud Run. Cloud Run is a serverless platform that automatically scales the number of container instances up or down based on the traffic, even to 0, which is highly cost effective. This allows each component of our MAS to be scaled, updated, and managed independently. For organizations seeking fully managed enterprise-grade runtime, Google provides the Vertex AI agent engine. ADK is designed for seamless integration with this engine, offering a direct path from local development to a scalable, secure, and production-ready environment with minimal friction. In distributed systems like this, observability is paramount. It's crucial to have centralized logging, tracing, and monitoring to understand system behavior and debug issues. Deploying on Google Cloud allows for easy integrations with Cloud Logging and Cloud Trace, which provides a unified view of a request as it flows through the A2A and MCP protocols across different services. Throughout this tutorial, we have designed and built a sophisticated multi-agent system from the ground up. The journey has revealed a core architectural pattern that is fundamental to creating robust, scalable, and maintainable agentic applications, a layered, decoupled architecture built on open standards. The key takeaway is the clear separation of role facilitated by our technology stack. We used MCP to act, standardizing the connection from agents to real-world tools and data they needed, and A2A to collaborate, standardizing the communication and delegation between the specialized agent, and ADK to build, providing the code-first framework to construct and orchestrate these components into a cohesive system. While this demonstration focused on Google's ADK, It's crucial to recognize the power of the open protocols that underpin it. MCP and A2A are open standards, not proprietary technology locked into a single framework. This means that agent built with other popular frameworks such as LangGraph for stateful workflows, Crew AI for collaborative agent teams, or Llama Index for knowledge-intensive tasks can, in principle, be made to speak these protocols. This fosters an open, interoperable system, preventing vendor lock-in and allowing developers to choose the best tools for each specific job while ensuring their creations can participate in a larger collaborative network. The field of agentic AI is evolving at an incredible pace, moving beyond monolithic curiosities and into the realm of practical, mission-critical enterprise systems. We are at the very beginning of this new wave of AI development, where the focus is shifting from the capabilities from a single model to the emergent intelligence of collaborative systems. The patterns and tools like ADK, A2A, and MCP are solidifying, providing the stable foundation needed to build the next generation of AI application. Now is the perfect time for developers, engineers, and architects to acquire these skills. The principles of modularity, separation of concerns, and protocol-driven communication are timeless, and they are now being applied to build the intelligent, autonomous systems of the future. The next step is to explore the official documentation, experiment with the code, and begin constructing your own agent societies. And thank you.